we just are given any three positive numbers, is it the case that we can make a triangle where the lengths of the sides of the triangle are, in fact, those three positive numbers? We know the answer is no by the triangle inequality. We know that a particular inequality has to hold. So let's tell whether a triangle can have the sides with the given lengths. So here we go. 6, 10, 14. Well, the way to check this is to look at all the possible sums of 2 and make sure they exceed the third. 6 plus 10 equals 16, and that exceeds the third. 6 plus 14 equals 20, and that exceeds the third, which is 10. And finally, 10 plus 14 is 24, and that exceeds the third, 6. And so the triangle inequality holds, which means we can actually produce a triangle, one side of length 6, one side of length 10, and one side of length 14. Neat. So the triangle inequality is sort of a handy little tool to have around, and in fact it's used all the time in advanced math. When I do my own mathematics, where I'm discovering new math, I'm using the triangle inequality all the time. Isn't this cool? We're sort of sharing a triangle inequality together. I like it. I like it. All right, let's try this one. Can we have a triangle, side lengths 5, 9, 14? Well, let's see if the triangle inequality holds for all possible sums of 2. So 5 plus 9 equals 14. Is that greater than the third side, 14? Well, the answer is no. It actually equals 14. So this is not a triangle. If you try to make it a triangle, here's what would happen. I'll try to draw it for you right now live. What you've got here is you've got a side of length 14, and then you've got a side of length 5 and a side of length 9. So if I put the 5 side here and the 9 side here, to get them to touch, they'd have to sort of collapse right onto this line. You see, here's the 5, and here's the 9. You see how they all have to line up perfectly? Because there's no room to have them bow out to make the triangle tip-top, rooftop thing. And that's not a triangle, that's a line segment. So in fact, the answer is no, we can't make a triangle out of this because the triangle inequality is not satisfied. I'm sorry, if you like those three numbers, we can use them for other things, but not for the lengths of the triangle. How about this? A minus 1, a squared minus 2, and 3a, where a is the number 4. That's a cryptic way of saying three numbers. Let's see if we can figure them out. If a is 4, a minus 1 is 3. If a is 4, a squared is 16, minus 2 is 14. And if a is 4, 3a is 12. And the question is, will this form a triangle? Well, we ask if the triangle inequality holds for all pairs of sides. 3 plus 14 is 17, which exceeds the third side, 12. 3 plus 12 equals 15, which just barely exceeds 14, but it exceeds 14. All we care about is if it exceeds 14. And 14 plus 12, well, that's 26, which is certainly bigger than 3. And so, yes, you can have a triangle that has these lengths. Very, very, very cool. The triangle inequality. Something not to be messed with. Let's see the triangle inequality in action and see that, in fact, that will actually give us potential upper and lower quantities for lengths of sides, so upper and lower bounds. Here is a triangle. We're told that this side is length 9, this side is length 5, but we don't know what this side S is. It could be really small, it could be really large. And we want to know upper and lower bounds for the largest that S could be and the smallest that S could be. Well, we can use the triangle inequality. And we can actually think about this sort of visually too. See, here I have the triangle, and one side is length 9, and one side is length 5. And so now, what are the possibilities? Well, see, there's lots of possibilities for S. S could be quite long, or it could be quite small. What's the smallest it could be? Well, imagine the degenerate triangle where we collapse this down. That's still a triangle, but now it's no longer a triangle. What would this length right here be? Well, that length would be 4, because if this is 5 and the whole thing is 9, this is 4. So as long as this side is a little bit bigger than 4, I'll actually have a triangle. That immediately tells me that S has to be greater than 4. Anything greater than 4 will work. But could it be arbitrarily large? Well, let's see. If we swing it around this way, what's the greatest that S could be? Well, notice that if we hit here, then these are actually in the same straight line again. We're in trouble. That's not a triangle. What would that length be? That length would be 9 plus 5, which would be 14. But if we have it just a hair under 14, that's a completely fine triangle. So the upper bound is going to be 14. So by the triangle inequality, we can see that S has to live between 4 and 14. And notice that it's strict inequality. We're not allowed to actually equal that. And you can see that if we had this thing, for example, be 4, if S equaled 4, then the triangle inequality would not hold, because 4 plus 5 would equal 9, and it has to exceed 9. So S has to be a little bit bigger than 4, and S can't be 14 or larger, because if it were, then the triangle inequality would not be satisfied, because then what we'd see is we'd see that 9 plus 5, which equals 14, would not exceed the third side, which would be 14. So really S lives in between 4 and 14, not including those values. But anything else is completely fine, and here's the range. Any of those triangles would work, even here. That's it. All right, let's take a look at some inequalities involving one triangle. So here's a triangle, triangle LMN. And notice that we're given the side lengths. And our mission is to write the angles in order from smallest to largest. Now this seems a little bit problematic in so many questions in math, because it seems like we don't have enough information. And that's the power of mathematical thinking and all the theorems we've been developing in geometry. They actually provide us with powerful tools that let us answer questions that on first inspection seem unanswerable. Well, the fundamental theorem that we're going to use here is that if we look at two sides and one side has a larger length than the other, then the opposite angles, the angles that are sort of opposite those sides, will actually have the similar size. So for example, I see here that this is the smallest side length. That means that this angle must be the smallest angle of all the triangles. This is the next largest length of the sides of the triangle, which means that the angle opposite here, L, must in fact be the next largest. And finally, this is the largest side, and that corresponds to the largest angle. So basically what we're seeing is the following theorem. That if I know that this side, AB, has a length that is greater than the side BC, then that tells me that this angle must be larger than this angle. So then the measure of angle C must exceed the measure of angle A. And using that property here, what I see is that since this is the smallest side, opposite it, in fact, is going to be the smallest angle. And so I see that the measure, so the angle M is the smallest angle, followed by the angle opposite the side that has length 22.4, which is angle L, and followed by the largest angle, which is angle N. So there I've written the angles in order from smallest measure up to largest measure. Neat. Great principle. How about this one? Here's a triangle, and the question here is, write the sides in order from shortest to longest. Well, again, we're having a similar issue here in that all we know are actually two of the angles. Wait a minute, we don't even have a third angle? Well, if you know two angles of a triangle, you always know the third, because remember, the sum of the angles of the measures of the angles of a triangle equal 180 degrees. If we take 68 and add it to 46, we get 114 degrees. We know the whole thing is 180, so I take 180 degrees and subtract 114. I see 56 degrees, which is this angle measure, and so automatically I get that for free. So that was pretty easy. But what about the sides? Well, a similar result holds. Larger angles are opposite larger sides of a triangle. So if you take a look at this, if we know the measure of angle Z is greater than the measure of angle Y, that means that the length of the side opposite here, XY, must actually be greater than the length of the side opposite Y, which is XZ. And let's see if everyone is happy with that. If everybody is happy with that, 5, 6, 7. Actually, let's see. Do you notice something interesting here? This really, if you take the sum of these two angles, we get 114. If we take 180 and subtract 114, we get what? We get 66 degrees. Did you see that? If you saw that, good for you. Good for you. Good for you. Excellent. Is everyone happy now? I guess so. All right. So yeah, so making a subtraction mistake is not good. But you can see how you can check your answer by adding these three angles up and making sure they're 180. All right, so now, the point here is that if the measure of angle Z is greater than the measure of angle Y, then the corresponding sides that are opposite these angles will be correspondingly large. So the side opposite Z will have a larger length than this side here. In particular, what I see is that XY, that length, is going to be greater than XZ, just as with the angle measures. And so here, since we know all the angle measures, I can tell you which sides, I can write the sides from shortest to longest. I look for the tiniest angle, 46, that's the shortest side, opposite. So DE, that side is going to be the shortest, followed by EF, because that is opposite the next largest angle. And then the last side, which is DF, is the largest because it's opposite the largest angle. So there you have it. We can actually figure out inequalities involving the angles or involving the side lengths just by knowing one. It'll give me the other.